Namaste, students. Let's start today's session with a simple question that you might have wondered about before.
Have you ever really thought about this? You know, when you take an aspirin, it just knows to work on your pain. Or an antibiotic, it only targets the bacteria, not all the cells in your body. How does a drug molecule know exactly where to go and what to do? It seems like magic, no? But actually, it is just pure chemistry. You see, the answer to this little mystery lies in a very fundamental concept in chemistry. It's called the collision theory of chemical reactions, and this theory is the key that unlocks how reactions actually happen, right down at the molecular level.
So why should we care about this topic? Well, understanding this theory helps us to design better medicines, create more efficient industrial processes, and it even helps us understand something as simple as why we keep our food inside the refrigerator. Cello, let's get into it.
Okay, so what is needed for a chemical reaction to actually happen? It is not enough for molecules to just bump into each other. For a reaction to be successful, there are two non-negotiable conditions that must be met.
These are the two golden rules. First, the colliding molecules must have enough energy. There is a minimum amount that we call the activation energy, or E subscript A. You can think of it like a minimum height you have to jump to clear a hurdle. And second, they must collide in the proper orientation. They have to be aligned just right, almost like puzzle pieces that have to fit together perfectly. Now, this brings us to a very common misunderstanding. Many students think, okay, simple, more collisions will mean a faster reaction. But listen, that is not the complete story at all. The reality is, the vast majority of collisions between molecules are, well, they're fruitless. They just bounce off each other without reacting.
So here is the most important thing to remember. A successful collision, or what we call an effective collision, is actually very rare. It only happens when both the energy and the orientation are just right. If even one thing is missing, not enough energy or the wrong angle, the molecules will simply bounce apart, no reaction. Only when both conditions are perfect do the old bonds break and new products get formed.
To make this idea of energy and orientation crystal clear, let's use a simple analogy. It's one that you can easily remember for your exam: the lock and key. Just think about it. The key hitting the lock, that is the collision. But just touching the lock is not enough, is it? You have to push the key with enough force. That is your activation energy. And even if you push with enough force, if the key is upside down or at the wrong angle, it won't work. It needs the proper orientation. Only when you have the right force and the right alignment does the lock finally open. This is exactly how molecules react.
And this is why the theory is so brilliant, you know? It connects the things we can see and measure in the lab, like how fast a reaction is, to the invisible world of what the molecules are actually doing. It gives us the why behind everything we observe about reaction speeds.
Right, let's build on this idea by creating a mental picture. Visualizing what is happening inside a reaction vessel is very helpful for understanding.
I want you to picture a crowded dance floor, maybe at a wedding party. All the people who are dancing around, they are just like our reactant molecules in a solution, moving randomly and constantly bumping into each other.
Now, if the music is very slow and the floor is not too crowded, that's like a system at low temperature and low concentration. The dancers are moving slowly, and the collisions are rare and gentle. But now, what if we increase the temperature and concentration? The DJ starts playing fast music, and you pack more people onto the floor. Suddenly, the dancers become very energetic, and they are constantly bumping into each other forcefully. This means more collisions will have enough energy to be reactive.
But you must remember the second rule. Even on this high-energy dance floor, if two dancers bump into each other back-to-back or at some strange angle, they just stumble and move apart. Nothing happens. It's only a face-to-face, energetic collision, a productive one, that might lead to a new dance partnership. And that is our chemical product.
Okay, so the theory sounds logical, but where do we actually see it in action? Let's look at some real-world examples, from the medicine we started with, all the way to the technology inside your family's car.
So let's go back to our first question about medicines. The reason an antibiotic is so specific is because of that orientation requirement. The drug molecule has a very unique shape, and it must collide with its target, say an enzyme in a bacterium, in a very precise orientation so it can fit perfectly, just like our key into its lock. If it collides with any other cell or at the wrong angle, it will just bounce off. Simple as that.
Now for a brilliant piece of technology. The catalytic converter in your car is a fantastic example of collision theory at work. Its job is to take the harmful gases from the engine, like nitrogen oxides and carbon monoxide, and quickly convert them into harmless nitrogen and carbon dioxide before they leave the exhaust pipe.
So how does it do this so fast? Well, without a catalyst, the activation energy for this reaction is very, very high. This means successful collisions are extremely rare, almost impossible really. But the catalyst, which is usually a precious metal like platinum, provides an easier route, a shortcut with a much, much lower activation energy. It's not adding energy, it is just lowering the energy hurdle. So now many more collisions have enough energy to react, and the reaction becomes incredibly fast.
Okay, we have covered a lot of ground today. To summarize everything and make it nice and easy for you to remember for your exams, let's just quickly recap the main points of this entire topic.
Here are the 3 most important things to take away. First, the core idea is simple. For a reaction to happen, a collision needs both sufficient energy and the correct orientation. Second, for a mental picture, just always remember the lock and key. It is the perfect analogy for this. And third, for a real-world example, remember that catalytic converters work by lowering the activation energy barrier, which is what makes the reactions faster.
Trust me on this. If you can just remember these 3 things, the main idea, one simple picture, and one real-world example, this whole topic of collision theory will become so much easier for you to handle in your exams. You will feel much more confident about it.
So, I will leave you with this one final thought. Now that you understand the rules of molecular collisions, can you see how mastering these rules is the secret behind creating life-saving drugs, developing efficient industrial processes, and engineering a cleaner environment for all of us? It all comes down to controlling collisions.